Today, we will continue on from where we left off on last Thursday. We'll actually talk about the remainder of one more thing that you have to do, or at least the assembly should be capable of doing, which is function calls. This is a part 3 of the x86 assembly, I guess, mini series of this class, right? So again, as we said, we will talk about function calls. So let's dive into that. So when you talk about a function call, right, what's supposed to happen? So anyone here remember our old friend ProgramCounter? Anyone remember that? What is a program counter? What is a program counter? Which has the same meaning as instruction, pointer, or the RIP inside x86. Exactly. Something that tells you which line to run, right? It points to the next memory address where the instruction is supposed to be located, right? This is where I'm gonna run the next line. So if I have a function call, what happened to my program counter? That's actually the high level overview, right? So today we'll go top down. We'll start from the high level overview of, hey, what's happening when we have a function call, down to the detail on what actually happened to the value of the register when we have to call a function. So at a high level, when you have a function call, what actually happened? Your code jumps somewhere, right? The code jumps somewhere, and what else do we have to do in a function call? Function sometimes take inputs, right? In many cases, some function take inputs. So the code jumps somewhere, and on top of it, the value inside the variable are being passed around from one function to another. And once you're done, another thing the function call is supposed to do is returning the value, returning something back, right? So from the code example so far that we've seen in the part 1 and part 2 of x86, what register should we store for me to return a value? Anyone remember? What is which register represent the return value in x86? Where do we put the return value? Anyone remember that one register that we use as a return value? This is RAX. We put that in RAX. Anything in RAX means that we're going to return that value. The code jumps somewhere. It means that the program counter is updated, but not with the current line, with the line of the first line in the function of where you want to call, right? And one more thing, when I return from a function call, do I go to the next line or do I go back somewhere? Can someone tell me? When I finish a function call and I am returning, do I run the next line or do I run something else? What is my next line? What is the next value for the PC? So let's say I have a code go straight down like this, and then a function call, and then go straight down, right? And this is the function. What actually happened is I go from here to here, reach the function call, then move to here, from here to go to here. When I have to finish the function call, what happened? When I finish the function call, what's the next line do I run? You go back, right? You go back here to this line and you resume the execution, right? One quick note that you should have in mind from this point on is whatever line you're going to run, the program counter should point to that line. The program counter should point to that line. Because once you have that mindset, right, it's actually what's happening in your computer. And on top of that, it's actually what you're supposed to do in assembly. In assembly, it would manage such that the program counter go exactly back to that line and it keep running. So the ability for me to go back to that line, what does it mean? It means that I have to store this address somewhere, right? I have to memorize it. Otherwise I can't go back, right? I have to memorize where I'm from. Otherwise I cannot go back. So that's the first thing that you have to remember for this lecture. You have to memorize where I jumped from. Otherwise, I have no idea where do I go back. Hopefully that's easy to memorize, basically. If I go somewhere, I need to remember where I'm from so that I can come back to that function. All right. So let's go high level, top down. What do we have to do? Generally, things that you have to do in assembly, in handling a function call, right? The first thing you have to do is called passing the control. What do I mean by control? What do I mean by control is this. This has to do with the control flow of how I run the program. Every program would follow some flow, right? If you have code like if else, it would branch things out, right? So passing the control means that I'm essentially passing the control of the execution to some function call. That is, we can use the name procedure code as like, hey, it's a function call, right? So you can point to the beginning of the function call, in this case, P, right? P call Q, which means that when you jump to Q, you know, hey, I have to run the first line, finish this, then come back and run this next line in P. So that's what passing the control means. Then you need to pass the data. Pass the data means what? I need to make sure that I has the correct value. So in this case, what should pass in? What value should be passed in to I? Can someone tell me what's the value that I should take? X, yes. It should take the value, whatever X is taking right now. I should have that value, right? The assembly code need to make sure this is maintained. And today we'll learn what are the specifications for that, right? Sorry about background noise. My cat is like playing behind me. So you might hear the bell jingling. The next thing you have to manage is memory management, right? You want to make sure you have handle things like this. I allocate the integer, 10 of them, for the variable v. One thing I have to make sure is I would make sure v is defined here. V is defined in here, but it cannot be used elsewhere. So if I'm in here and refer to v, that should not be legal. If I'm in here and I say, hey, v10, no, it should not be legal, right? It's outside of the scope. So it should allocate something as needed and deallocate your variable upon return. It should not be referable. It should not be, you should not be able to reference that variable name when you finish the function call, right? And you have to make sure it's machine instruction. Basically, it's follow the assembly syntax, right? So again, here's the highlight of what does it mean by passing your control. The red part is when I jumped to the function call. The blue part is when I return back. I need to be right before I call another function called print y, right? Passing the data means x should go into I, return sorry, return vt should go into the value called y at the end. It has to have that management. Then when you have the memory management like Reentrant over here, it should be managed by the assembly. Right? Assembly should make sure there's a part that manages this. There's this thing called application binary interface, ABI, not API, ABI, not application uh, programming interface, but application binary interface that dictates what do you have to do. How do you implement the mechanism for passing the control, passing the value, and also handle memory management. The choice of how do you implement this are determined by the designer. Most of the time, these are actually you as a programmer, the OS, the compiler, and the people that would dictate what can be called and what cannot be called is the architect. Right? From the hardware up to the programmer, they will work together and see, okay, how do I implement the way I call the function? How do I implement the way that I can translate the function call in Python into assembly, the function call in Java into assembly, the function call in different languages into assembly? Because at the end of the day, that's what the machine understands. All right. So let's now dive into x86. And today we'll talk about major, like two things in particular, the stack structure and the calling convention. The calling convention basically is it dictates what you're supposed to do when you have a function call, right? This would allow you to have your code working, like your assembly code working with other people, as long as you follow the convention. So let's talk about the x86 stack, right? So the first thing we will talk about today is the x86 stack, and here is what it looks like. x86 stack is a region in the memory that are managed by the stack discipline. Can someone tell me what's the stack discipline? What's the guideline of using the stack? What is a stack? All right, recall before the midterm. What is a stack? What's the major principles behind using a stack? Last in, first out. What else? What are the main two command I can do with the stack? You will take the first or put in, yes, you have push and pop, right? You can push things in, pop things out. So this is the stack discipline. This region of memory is managed, and then use a stack as a data structure for this region. When you buy DRAM and you plug it in your computer, what would happen is when you install Windows, Linux, or Mac OS, they would separate out your memory into different region based on the ISA. The ISA is what dictates where do you put things, including your data, your program, and anything that want to use the memory, including even things like the monitor interface with the data itself, right? So x86 is one of the ISA, and it uses stack to maintain function calls. The memory itself, again, still is viewed as array of bytes, right? You can access each addresses and is separated into multiple regions. Some of them would have the code, your program would be in there. Some of them would be dictated and specify that, hey, these are read-only data. A raw data that you put in, it should not be modified because it's marked as read-only. Part of this is for the stack. And here is how the stack looks like. There's a top of the stack. That's where you keep pushing thing in. So you interact with the top of the stack. You push thing in or you pop thing out. And it starts from somewhere. I'll call this the base. The base of your stack is where you put in the first item. The base is where you put in the first item. The stack pointer point to the top. The stack pointer point to the top. Any questions so far? And these are all the memory address. These are all the memory address. It's somewhere in DRAM. All right. And in x86, the way the stack grows, so let's say you push something in, it grows down. So the address goes up. The address would go up. So let's say this is address 10. It's going to be address 10, 11, 12, 13, 14, 15, blah, blah, blah. It keeps growing up. When you add something to the stack, these things go down. The address 10 would, when you push things in, then you add something to address something that's less than 10, right? Remember this, it grows down. The base of your stack is at the highest address. The top of your stack is at the lowest address. Why do we care? This is gonna reduce your confusions quite a bit when you read assembly code in the exercise, including the sample code we have right here, right? And again, there are two commands, push and pop, right? You can push to the stack and pop something from the stack. So let's go through the first command, push. This is actually the second part of the assignment 3. We actually don't ask you much. We ask you to convert the push, different version of push into different binary, just ones and zeros. So it's actually pretty easy, just the conversion of the command into binary, right? It should be, in the end, giant switch case or if-else statement. As simple as that. So the push, what does it do? Let's say you want to push a value into the stack, right? Where is the next empty place I can put it in? Can someone tell me where's the next empty place I can put things in? Can I put it in here, number 1, or do I need to put it in number 2? Number 2, right? That's the next empty space. So in order to refer to this location, I first need to decrement RSP by 8. Why 8? These are 64-bit machine. When I say push Q, these are for 8 byte. So I would assume my source, this value is 8 bytes. So I need to make the room for 8 bytes of data by decrement RSP by 8. So now it's going to be RSP minus 8. That's the new RSP. Then you write the value to there. So this is basically what happened. The first step, decrement RSP by 8. So you can now refer to the next empty space and put the value there. So now you put the value in there to make sure that the value is now on the stack. All right. The next operation is pop. The next operation is pop. What does pop? Oops, sorry. What does pop do? Pop pops the value out of the stack. The next thing after you pop RSP should point to the next item. So you increment the RSP by 8, right? A quick note is I popped the value out and I didn't actually clear the value. So the value got popped out, but over here there's still value in there. Why is it okay? It's actually okay because as long as you manage the stack correctly, these values inside the stack are not going to be referred to. So it's safe to put it there. You save some operations. It makes your computer faster. You don't need to clear what's the value in there. All right. So now let's talk about our function call. Now we know how the stack work in x86, which work like any normal stack. The next thing we have to talk about is the function call, right? So function call has 3 main parts that we are going to talk about today. How to manage the program counter, how to pass the data in and out, and how to manage the local data tied to each function. Other ISA can handle things differently. So a quick note that this is for x86, which is again still the most common ISA in the world. All right. So that's why we stick with x86. So let's first look at the code example. The next slide will have a bunch of code. Well, actually it's have just a few lines of C code, but a few more lines of assembly. First, let's look at the C part. Can someone tell me what does the function do? What does this function do? And what does this function do? function A called mul_store and function B called mul2. So let's go to function B first. Mul2, what does it do? Someone tell me, look at the C code and look at what are they supposed to do? What's happening here? What do I return? It take in two long integer, multiply them and return. Simple, right? So if you look at the assembly code, also really simple. So if you assume that the first variable here is in RDI, B is in RSI, in a bit, you know why can I make that assumption. It's actually part of the assumption that will happen in x86. The first argument is in RDI. The second argument will be in RSI. So in this case, the first thing I do is I put A into RAX. So now RAX is going to equal to A. Then I multiply A with B. So now RAX is going to take A multiplied by B. All right. So any questions about this function, mul2? Because then we'll now jump to mul_store. What actually is going on? What actually is going on? So what register should store X based on our assumption? I mean, when I go into this function, what register should have the value X? If you look at this convention, you see that it's in RDI, right? RDI, yes, exactly, RDI. RSI will store Y. So that's the assumption that x86 program will make. The first variable in RDI, the second variable is in RSI. In our in-class exercise, we use an older version of GCC and the 32-bit version. So that's a little bit different. I'm going to talk about this toward the end of the class. But for now, RDI and RSI is where you store the first and the second variable. All right. And when I call this function x and y, where should I make sure I store the value x? I should make sure RDI has x and RSI has y, so that when you call the function, RDI over here has x and RSI has y, so you can finish the multiplication. All right. So that's why if you look at the assembly code, I did not modify RSI. I did not modify RDI because that's where they're supposed to be. It already has the value that I want them to be. What is unique is there's another variable called def, which is our definition, right? This is going to be in, right? This is going to be in RDX. This is going to be in RDX. Then if you look at the code, right? If you look at the code, there's something that has to do with RDX and RBX. The first thing is I will put RDX into RBX. So basically make sure that our variable def, right, our variable def is now in RBX. So now RBX equal to def. And then I call the function. After I call the function, what register name should have my value, which is x multiplied by y? It should be in what register? Look at the green box, and where do I store my return value? IX. And it's actually in RX, right? So I put the result of my mul2 into RAX. So the next instruction is I store that result, which is this line of code, right? This line translate to this. I store the result of the multiply into where this is located. So this basically store this equal T. Why do I have to push and pop RBX? Why do I have to push and pop RBX? Because my function use RBX, these make sure that if someone else already used RBX before, I save it for them. We'll talk about this in a bit. We'll talk about it actually in the next slide. We'll talk about this in the next slide. I don't want to talk about it here because I have no room to draw things. Right? So let's talk about this. Let's say I have a function called P that called a function called Q, right? I call this function somewhere, Q is here, right? And let's say in this function, I use RCX, I use RBX, and then I also use RDX. These are registers I can use, right? And in a function called Q, I also happen to use RCX as well. What's the problem here? If the function called P, I have the value of RCX to be 7, RBX to be 10, and RDX to be 9, right? And in function Q, I use it for a totally different purposes, and now it has the value 4. What happened? What happened? What are the wrong, like potentially wrong things that can happen? RCX, right? RCX gets modified by Q unintentionally to 4. When I return and come back, right? When I finish Q and come back to this line, somehow RCX is 4. So what can I do? What should I do to prevent this from happening? To prevent this from happening. I need to save it, right? Someone, either P or Q, have to save this. Make sure that when I come back, RCX is 7 and not 4. How do I save this? Where can I save this? Where is the place I can store value? Can I save it in the memory somewhere? Can I save this value 7 that owns by RCX somewhere in the memory? Is that a yes or a no? Any guess? Yeah, right? It's totally possible. Then one easy way I can do is I can push RCX and then I can pop RCX, right? Is it okay? So let me ask you this. Is this okay? My function that I'm calling happen to use RCX and I don't want to, I want to make sure that when I finish, I return the old value of RCX. So I first push and when I'm done, I pop. Is that okay? It looks okay, right? And it actually is okay. So let me go back one slide. And see our sample code. That part is happening right here. The reason why you push and pop RBX in the beginning is apparently when I generate this assembly, the function that called mouse store happened to use RBX, right? So I will save it. So yes, in this case, to answer the question on the chat, RCX is now stored. It's saved on the stack. So that when you finish using RCX, you reverse the data of RCX back, right, back to the old data. How does the RCX remember the old value? The problem, it does not. You as a programmer have to save the old value. When you in Q, right, over here RCX is still 7. Because you call the function, you did not modify RCX. So when you call the function, the first thing that happened, all the register files is still having the old value. So you save it in the stack. Then you modify RCX any way you want. Afterward, RCX becomes 4, and you finish the function call. Before you return, you pop so that RCX is 7 again, right? So in this case, it push 7. Then you modify Q, do whatever with RCX. I'm done. I popped. I popped to make sure RCX is reverted back to 7. All right, is this clear? And if you look at assembly code, right, these depends on the compiler. It depends on who write the code. In most x86, Q is the guy who is supposed to push and pop. But I've seen instances of this being done in P. Sometimes it's done by the callee, sometimes it's done by the caller, right? The person that calls the function can also save this. Which one is better? Depends. Which one is better? It depends. Personally, I believe the way it's done here, having Q push and pop is better because Q knows what are the register I need. So I just save whatever I need and that's all. All right. So that in that way, I don't have to save every single thing in the world. All right. So now let's go back to our example, right? And I'll show you what happened to the stack as well as our program counter. RIP in x86, this is the program counter. The program counter. All right, it points to what line we're running. So let's say we are right here. Let's say we're right here. The program counter is going to be at 400544 because that's the current line. That's the current line. So I call the function. Let's say I call the function. What should be the next value of my program counter? I say call Q 400550. What should be the value of RIP? What should be the next value of RIP? That's the next line I'm running. So what's the next line? What's the address? 400550. You're correct, right? So it should point to this line. All right. So the next question, I need to be able to come back, right? I need to be able to come back to what line? Once I finish the function call, where do I have to come back? 400549 actually, because we are done with 544. So the next instruction should be 549. How do I make sure that happen? I will put 400549 right here. I'll put 400549 right there at the stack pointer. Right? This would make sure that when I finish the function call, I can pop and go back, right? And go back to 400549. This is actually what happened when you have the call Q instruction. Call Q will first update the program counter to 400550 and put this to the stack, which is this, right? You update the stack with the next line. You decrement RSP so that it points to this top of the stack. And then program counter is now taking this value. So you can keep running. You keep running until you're at 400557. Now you have the return instruction. Where should the program counter be? If I run this return instruction, where should be my program counter? Where do you go back to? It should be whatever this value is, right? This would replace this. So you are going to have x0x400549 in the program counter. Then you will update the stack pointer. This would become 0x120, which is this line again. You pop, basically. You pop and put whatever is on top of the stack pointer into the program counter. That way, you can return back to this next line. That way, you can return back to the next line. Any question? Any question? Yes. The question is this done automatically with the combination of call queue, return queue? This is going to be done automatically for you. All right. It's actually awesome. It is done automatically for you. Just pair this with, like, you do call queue and return queue, and that will be handled in x86. When you return queue, make sure that the stack pointer point to where you want to return. When you call return queue, make sure the stack pointer points to that address. All right. But otherwise, the rest is done automatically. Okay. So now we are going to transition into how does x86 manage passing data in and returning data comes back out. Because it's a transition into the new concepts again, right? Let's do a 5 minute break. Is that okay? We will resume at 2:50. We will resume at 2:50 and we'll come back and talk about how do I pass data around. Okay, so I'll pause the recording so that when you watch the video, there's no break. You can keep watching. You can pause at your own pace. All right, so let's resume our lecture and now talk about what would happen when you have to pass data into the function call, right? This basically would govern how do we manage function as an input that are going into the function, and how do we store the return value. And this is actually a lot simpler than you imagine, because these are assumptions that are going to be made, right? So for the purpose of this class, and most of the x86 64, the current version of x86, the first argument, let's say you have a function called, I guess, sorry, let me name a function, some int, right? Some function, int I, int j, int k, int l. In this case, there are 4 inputs. The first input, I, will be in RDI, j will be in RSI, k will be in RDX, l will be in RCX. The next input, if you have the 5th input, would be in R8. If you have the 6th input, would be in R9. Anything more than 6 argument will go into your stack. 7th input, 8th input, 9th input, blah, 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 up to nth input will go to the stack. So in this case, if you want to pass in 8 variables to your function, the first 6 will be in the register. The next 2 will be on the stack. If you want to return, that will be put in RAX. And here's some example. I have 2 functions, mouse store and mouse2, the same function again, right? In this case, you might have noticed that the mouse store, you have X and Y and C. In this case, X is going to be stored in RTI. Y is going to be stored in RSI. And that, which is the last input here, will be stored in RTX. Right? And when you call this function called mouse2, it takes in X and Y as an input, store X in A, Y in B, right? So in this case, A is going to be in RDI, B is going to be in RSI. And again, when you want to return, you put S right into RAX. In this case, T is in RDX. So basically, whatever you're trying to return will be in RAX. All right, it's as simple as that. Any question? Any question? These have to be done by the caller. This is not done automatically. Whoever called the function need to do this for you. All right. Whoever called function called mouse store need to make sure X is in RDI, Y is in RSI, Des is in RDX. In this case, when mouse store call mouse2, A is already in RDI, Y is already in RSI, so you don't have to do it again. But generally, this is done by the caller. All right. So now the next set of things is how do you manage local data, like things inside the function that need register or things that are tied to each function call, right? We use the stack to do this as well. Many languages are stack-based languages like C and Java, right? The code must be having this property we call reentrant. Reentrant means that I call some procedures, which basically means a function call. You can have multiple instantiation of that function call. Fibonacci, for example, I would call fib of n minus 1 plus fib of n minus 2. That's multiple instantiation of the function called fib, right? When you finish one instantiation, it should come back to that line you just finished. So that's why we call this reentrant. It comes back to where you have the function call. So this means that for each function call, or for each procedure calls, you need some place to store everything related to that particular function call, such as the input arguments, the local variables that you need, and the return pointer. These are stored on your stack. These are stored on the stack. So the stack discipline is this. For each procedure calls, you would put things in the first in, last out order. The first in, last out order. And you allocate more frames. Basically, there will be a frame for each function call. One frame for single procedure instantiation. In other words, one frame per one instance of the function call. So let me visualize this. I can have a code. The first function is called U that has a function call called who. Inside who, there's two instances of mi. Inside mi, you have the recursive function that call itself. And this is the example call chain. I start with U, which then call who. And who call mi twice, like once and twice. This is the first time this get called. This is the second time this get called. Then when I'm in mi, the first time you call mi, I call it 2 more times. So who mi. Then I'm done. I call another branch of mi function. But let's say this is the assumption we have so far. All right. Let's assume this is the assumption we have so far. I then need to make sure for each function call for mi, these are uniquely tracked because each function call has its own local variable, right? This is similar to how fib of 45 is different from fib of 44. It's a totally two different function call, right? So in this case, I have to track different instantiation of the mi, the function call mi. How do I do that? I can use the stack. Now that I told you each function call is tied to a frame, right? It's a function. Function 1, function 2, each one of them is tied to one frame. Inside the frame, what should be in there? Where do I return? Return information. Local storage if you need one, or any temporary space if you need one. So when you call the function, the caller, the function that call another function have to set this up. You set up the stack for the next function you're calling. These are called setup code. That's where you set up the input, for example, making sure The first input is in RDI, the second input is in RSI, the third input is in RDX, etc., etc., etc. Right? Then you deallocate. When return. You finish the code. There's a part at the end of procedure calls that would finishing up that include the return call. I return from the function call. There are two registers involved with the stack. This one you've seen already, the stack pointer. What does the stack pointer do? It points to the top, right? It points to the top of your stack. The second register that we have is the base pointer. The base pointer, the only purpose is to point to the base of the current frame. It points to the base of the current frame. Why is this a good idea? These allow you to basically, when I finish the function call, I know exactly where is the previous frame. I would know exactly, hey, the previous frame is right here. So let's go through our example. I have the function called u, which call the function who, right? So when I call the function who, I would then add the function who to the stack. I update the base pointer and the stack pointer so that it encapsulates the frame for the function who. Then I'm going to call the function mi, which call the function mi, which call another function called mi. In this case, you see that there are 3 frames. Each one of them ties to each version of mi function call. RBP again point to the base of the current frame. ISP point to the top of the stack pointer. So when I finish this recursion, I would pop, and go back to the earlier frame, update RBP, update RSP. So make sure that now I'm pointing at the current frame. Then when I'm done, I'm going to pop, like finishing up code to pop everything and go back to the earlier frame. Again, when this is done, I'm going to pop like everything and go back to the earlier frame. And now I am ready to run the second part of the function mi, which is what is a circle, right? So now I have another instantiation of mi. I push. And then when I'm done, I pop everything again so that I'm back to the function who, which when I'm done, I'm going to pop again so that I can go back to the function u. And then when I'm done, I'm going to pop everything to go back to whatever function called this weird function u who am I. All right. And this is done through assembly code and the combination of call and return. All right, so this is basically how the stack frame would look like. So the caller frame should have, for example, the arguments that you want to put in as an input. If you have more than 6 inputs, you put it there. Then you call, which means that you're gonna put in the return address. Then, in most cases, you would put in the old value of RBP. Why is this good? This allows you to restore the old RBP, which now point to here, this old RBP. So that when you call when you finish the function call, you can revert back to the old RBP. And when you call the function, you're going to save all the register, including any local variable, so that you can pop, like pop RBX, pop RCX as needed. As long as you do this properly, your program will run. As long as you do this properly, your program will run. Now we're going to show an example of a real program, right? The first function call is simple. I increment, I take in a pointer, takes in a value, and then I add value to that pointer. So basically, let's say if p or if star p point as the value 10 and value is 5, at the end, star p is going to equal to 10 plus 5, which is 15. which is 15, right? And the assembly code is simple here, right? RDI would take the P, RSI is value, RAX is our return value. So you put the return value, you start with star P, then you do star P plus val, and then you basically return, right? You return, and you store star P plus val at star P, making sure that is updated. All right. So that's our function called increment. I have the address. I increment the address by val. I have another function, which is also really short. What it does is it has a static value here, 15213, and it called the increment function. It called the increment function. So what this really do is this would make v2, right? v2 would be 18213. 18213. All right. You increment whatever 15213 is pointing at, add 3000 to that, and return 15213 plus 18213. That's what the code is doing. Here is the assembly of the code. So let's go through this line by line. Right? Let's go to this line by line. Initially, my RSP is pointing to the return address because I just go into the function call. The first thing I see is the return address. If I finish, I can return. If I finish, I can return. The first thing I do is I subtract 16 to RSP. What does this do? RSP would now point here. This is RSP minus 16. Basically make two box right here. Make two box right here, not being used so far. Now, you store 15213 at RSP plus 8. RSP plus 8. So at the moment, this is where RSP is. So this is going to be where RSP plus 8 is. So you store 15213 right here, right? So we are now done with the first two lines. This is what the stack is supposed to look like. After the first two lines that I highlight in the red color here, the stack is going to look like the bottom here. Now I'm going to go through the next line. Move out 3000 ESI. Move out 3000 ESI. Basically, I'm going to put 3000 into RSI. The reason why this get convert to ESI is because GCC detects that you can use 32-bit for this. No need to use 64-bit. So it can be more compact and a little bit better utilization. All right, so you move 3000 into RSI. Why do we need that? Our increment function, this is going to be RSI, this is going to be RDI. So the first thing I have to make sure is when I call the function, RDI should have the first input, RSI is supposed to have the second input. So now RSI has the 3000. RDI, right? I do LEAQ. LEAQ would get the address of RSP plus 8. Basically, this is going to be this address. Which is ampersand V1, address of where V1 is located. So now we just finished preparing the input for increment function. This prepare sorry, too close to each other. Let me rewrite this part. This prepare RSI. This prepare RDI. Once you finish doing this, we call the increment function. You know that the first input is going to be in RDI. We also will know that the second input will be in RSI, right? A quick note, the first note is ESI. Why ESI? Because 32-bit works more efficient. In this case, GCC figure, hey, we can use ESI. Why LEAQ? In this case, we actually use it to compute the address of RSP plus 8. The address of RSP plus 8. So now let's go to the next line. Let's go to the next line. I call increment function. I call the increment function. What will happen? Increment would store 3000 plus whatever this address. So from 15 to 13, you add 3000 to this. So you're gonna result into 18 to 13. You will result in 18 to 13. That will be in RAX. Now RAX is gonna have the value of basically V2, which is 18 to 13. So what are the remaining things that we have to do? What are the remaining things that we have to do? First of all, the RAX, as I said, RAX has a return value. This is going to be 18 to 13. You want to add V1 and V2 together. You want to add V1 and V2 together. What is V1? So this is how you add V1 and V2 together. You go back, look at RC plus 8, right? It's right here. You add that, so you're going to have V1 plus V2. Then you update the stack pointer. This is basically the cleanup code, right? To update the stack pointer, the stack pointer. So now RC point to the return address before you call return, right? Before you call return. So when you call the return function, here, RSP is here. So you know that you're going to return back to whatever function is being called earlier. So this is the final function call. Now ISP would point to the older frame. ISP will now point to the older frame. You return from the function call and you're done. So this is the summary of today's lecture. The important point is this. You have the caller frame and the callee. Typically, right, all the arguments are being put here. All the arguments will be put here. And then the return address will be put next, followed by RBP, the old version of RBP. And then if you need to use anything in the stack, you can keep putting it in. RSP will be updated based on that. And if you have another function call, then you push whatever you want to store for the arguments for the input. And the return value will be in RAX. The return value will be in RAX. So that's the general guideline. And that's it for today's lecture, because we have quite a long in-class exercise today that govern how to read assembly code. That includes function call, that includes stack management, and that also includes the jump table that we have from last Thursday. In the next lecture, we will transition into the next big topic, which govern memory and caching. These actually have a lot to do with how to write a fast program. We'll talk about how to make the data access fast. A lot of time you need to access a lot of data. In modern day workload, there's a lot of application demands a lot of data. How to make it fast. We'll talk about how does the OS prevent illegal memory access. How many people here got sick of segmentation fault? Can you raise your hand for assignment 2 and you got sick of segmentation fault? How many of you have that feeling already? I'm so sick of it. So we will talk about why is that good. It's actually a good thing to seg fault rather than you go and access someone else's data that can crash your machine, right? It's better to crash a program than crashing your machine. So segmentation fault has to do with virtual memory management, also The virtual memory management has multiple other benefits. We will talk about that starting from the next lecture. On top of this, we also talk about midterm solution. So we'll go through the midterm questions and talk about how do we approach each of the questions. The midterm exam is being graded the I think 50 something, so it takes some time. Sorry, take longer time than I thought. Also, assignment 1 is almost done grading. Assignment 2 is getting there. Each one of these should be updated as soon as possible. Should be out gradually by the end of the week. Before we leave today, we have in class exercise 10. This is written, and this can be confusing. Primarily is the assumption we have in the assumption. First, second, third, blah blah, blah inputs are on the stack. So there's a subtle difference between these in-class exercise and this lecture. The in-class exercise use an older version of the compiler. So instead of putting RGI and RSI as the first and the second input, etc., the first input is already on the stack. So it's not the 7 input, it's the first input, the second input, the third input. So if you look at the stack, it's going to be something like this. Old RBP, return address, argument 1, argument 2, argument 3, blah, blah, blah. And each one of this, because it's 32-bit, each one of this is 4 bytes long. It's 4 bytes long. So let's go over there and do some practice, right? This class, the assembly, you need practice. You need to actually go through them, go through the mess of how do we understand what's going on, right? So let's go through that together. I'm going to be on Discord. I'm going to wrap up the lecture portion of today a little bit earlier so that we have more time on Discord session. If you have any questions about assignments 3 as well as the in-class exercise. One last thing about our assignment 3. How many people have begun to read the assignment already? How many people check it out already? Anyone? So for those of you who read, okay, first of all, it looks horrifying, but it's not too bad. One thing I'm going to warn you is please read this early. This is different from assignment 2, where assignment 2 is a lot of coding. It's coding and make sure it compile and make sure it run. And yes, please use Linux environment to make sure you check your code with Linux environment. The thing about assignment 3 is it's just a little amount of coding. So the amount that you have to type is really small, but it requires longer thinking. You think a lot about how to make this work, and you put in like 1 or 2 lines or 5 lines of code for each of the subtasks, and you're done. So my recommendation definitely is check out reading, because if you don't know how to start, that's where the Discord session comes into play. I'm gonna be there. Ask me a question. How should I start over this? Doesn't mean longer due date because we have shorter typing. It doesn't have to type a lot. We just think a long time, and hopefully you what's going on, and then you have the answer. All right. Once, so I guarantee you. So let me stop the recording. So I'm gonna